Thank you very much for the presentation. Yes, this is a tool paper. It won't be really an interactive tool demonstration. Unfortunately, it will be just presented. Um, and the tool is called S2S, and this is a SQL to Stream is an automatic benchmark generator for the Java Stream API. Yeah, our work I've done in collaboration with Andrea and Walter, my advisor. So I will first quickly introduce the Java Stream API, which is basically a library that allows user to manipulate sequences of elements, of objects or primitives in a functional style. So, but when we use the Java Stream API, we are basically expressing our computation as a pipeline of operation. So every stream always starts with a stream creation operation. For example, we create a stream out of an array of objects or a collection. Then we have a sequence of intermediate operation. For example, we can map a function or a filter by a predicate. And finally, each stream always terminates with a terminal operation, which is actually the operation that produces a final result. For example, we can apply an aggregation function on the elements in the stream. The benefits of using the Stream API is that they provide a very concise styles that clearly improve readability and maintainability, but also it easifies parallelization because the Stream API can automatically split the computation into four-join tasks. The drawback of the Stream API is the performance. Indeed, it is known that often using the Stream API leads to a performance degradation when compared to implementing code with imperative code. For this reason, there have been proposed different tools in the research community that basically automatically convert code that make use of Stream into code that make use on the imperative code that make use of loops. However, there is a lack of benchmarks for the Stream API, and indeed for this reason, all these tools have been evaluated on micro benchmarks that have been manually selected by looking at existing code or manually implemented. So the problem that we are addressing with our tool is indeed the lack of benchmarks that are fully dedicated to the Java Stream API. Most of the existing Java benchmarks, for example, the well-known Da Capo, do not evaluate the Java streams at all. And to the best of our knowledge, there is only a single benchmark suite that evaluates a few stream, which is the Renaissance benchmark suite. But actually, there are only three very simple workloads for the Stream API. However, it is clear that both researchers, but most of all the Java language implementers, needs benchmark to internally optimize this library. It is also well known that designing a benchmark from scratch is a very tedious process that usually requires a lot of engineering effort. So the solution we are proposing to address this issue is based on the idea that the Stream API is basically a data processing library, is pretty close to Link actually. And many data processing benchmarks already exist in the data processing community. For example, the database community created many benchmarks for the SQL language. In this context, a benchmark is usually implemented as a dataset or a dataset generator and a set of SQL queries. For example, the GPCE benchmark. The goal of our tool is basically based on the intuition that the Stream API, expressing computation with the Stream API, is often very, very similar to expressing computation with SQL queries. So we believe that reusing existing SQL benchmark for stressing the performance of the Java Stream APIs is really a natural solution. So for this reason, our proposal is to automatically convert existing benchmarks or existing SQL queries into Java code that make use of the Stream API. So this is indeed the call of our tool, SQL to stream. Before entering into the details, I will quickly recap how a query is executed on a database system. So before query execution, a SQL query is parsed and converted into a query plan, which is basically an abstract syntax tree representation of the query. Then traditional database system interpreted the query plan exactly like a language, an interpreted language interpreted the abstract syntax tree of a program. Modern relational database are based on compilation. So a query is as soon as a query arrives, is immediately compiled into machine code and evaluated by running the machine code to optimize the performance. S2S is a tool that is basically a query compiler that compiles a given query plan into Java source code. So we are not targeting performance. So performance query execution, we are addressing the problem of creating plenty of Java code that make use of the Stream API. So we can execute a given query by converting it first into a query plan, then into Java source code, and then we can evaluate the Java code. The queries which are generated with S2S after converted to Java source code are tested to prevent bugs in the tool, actually, by comparing the result with an existing SQL engine, which is Apache site. And finally, they are wrapped into JMH benchmark, where JMH is a tool, very used tool to evaluate the performance of Java code. S2S is currently available on GitHub as open source code. Here we can see an architectural overview of the tool. So the input of our tool are a JDBC URL for a DB connection. For example, it can be even a SQLite dataset or any database for which exists a JDBC driver, and a SQL query. The tool connects to the database via the provided URL. It reads the table schema, and basically it generates Java code to handle the data which is in the database. Basically, the first step is converting the data into the database into Java objects. Then we convert the input SQL query into a query plan by leveraging an existing tool, again, site. Then the most important part is the query compilation, when we convert the query plan into Java source code that make use of the Stream API. And finally, we generate JUnit test and JMH benchmarks. Our SQL compiler is based on this conversion table. Basically, we visit the query plan, and for each node in the query plan, we generate a method call into the Stream API. So the table scan operator, which are the leaves of the query plan, are those nodes that loop over the table, basically, are converted into a stream creation method, the stream of in particular. And then we map the projection. Projection are basically a map operation in the Stream API. The predicates are a filter operation, limits as an equivalent operation, sort as well. Aggregation are a bit more tricky, and as we will see in a minute, and they are converted into a call to a collect, which is a terminal operator with a custom collector. Then we support two kinds of joins, the nested loop joins and the hash joins. In both cases, we basically append to the code of the right side of the join a flat map operation, which take care of finding the matching pair. And on the left side of the join, we use a to-list operation in case of nested loop joins, and we collect with a group by collector, so we create an hash map in case of an hash join. As mentioned, the aggregation is the most challenging operator for our conversion. And this is motivated by the fact that in SQL, an aggregation is defined by a list of aggregation functions. For example, we can select the minimum and the average of two different fields in a given table. However, there is no interface in the JavaScript API that allows to do so. We can select the minimum from a certain stream, the average, but not both at the same time. So for this reason, we indeed compile aggregation into a collect, into a mutable reduction, but the generated code for the collector itself is basically imperative code because there is no such an interface in the Stream API. We remind the paper for more detail because there is no such time. By leveraging the tool, we converted an existing set of queries and we created the first benchmark suite for the Java Stream API, which is BSS. BSS is composed of 8 rather simple queries and the dataset of the TPCH benchmarks. Among these queries, 7 come from the Stream Fusion engine, which is an existing work, and we added the last query as a more complex query so that we can show most of the supported SQL operators in a single query that we will also use as a sample. So this is, we can now see an example of query compilation. We have a rather complex query. These are actually split into 3 queries to facilitate the reading. So we have first, we create a virtual table called top orders, which are basically the top 1,000 most expensive ordered after a certain date. And a second virtual table, which is the fast ship item, basically the items within single items within an order, which has been shipped a single day after the order date. Then the main query selects the sum of only the items joined by the corresponding order. So this is the query plan for this particular query. The top orders are basically a scan over an order table, a filter over the order date, which are then sorted by price and finally limited. The fast ship items are simply a scan over the items table and a filter over ship date. And the word query basically joins these two subquery and aggregates the result with the sum aggregation function. This is on the left, this is the code generated by S2S for this given query. So let's go step by step. The left side of the join is first converted into a stream of the orders table. This DB orders is the one generated in the first step, the in-memory database. This is actually an array of objects of a type generated at runtime. Then we apply filter operation, the sorted operation, and the limit. And we implement the left part of the join by introducing a group by collector, which creates an hash map where the keys are the type join key, which is the type of order key, and the rows, the values in this hash map are a list of orders. So in case the order key is actually a key in the database, the list always will contain one element, but since we cannot know that, we always generate a map with this shape, so a list of rows on as values. The fast ship item virtual table is converted simply into a stream from items filtered by ship dates. Then the join itself is implemented by appending a flash map operation, which retrieves, basically defines the matching pairs by performing an hash lookup on the hash map, which indeed gives us a list of orders, and then we map a generated function, which basically selects the fields of interest. In this example, is only the field price. And finally, we append the code for the aggregation function, which is in this case is a sum operation. The main limitation of our tool is that we partially cover the stream API. This means that even if a set of queries are converted with our tool, if these queries cover all the SQL operator that we support, there will be some method in the JavaScript API that will never be called. However, it is worthwhile to note that the operation that we cover are the most relevant one in the context of data processing. And actually, by analyzing the whole stream API, we noticed that there are only two methods that make little sense in SQL, so also for S2S, which are take while and drop while. Because these methods are defined for to work on ordered sequences, but SQL tables are multi-set, they're banked, so they are not ordered. So at the moment, we do not cover all the stream API, but these two, the ones that we are not covering can be covered in the future. Take while and drop while are not an option for our tool. In conclusion, we propose that a generative programming technique to create benchmarks for the JavaScript API, and we implemented S2S based on this technique to convert SQL queries into Java source code. And with S2S, we generated the first benchmark suite for the JavaScript API, which is also available online. Thanks to S2S, many existing SQL benchmarks can be easily converted into benchmarks for this JavaScript API. As a future work, we first plan to address the mentioned limitation by implementing a conversion also to the other missing operation. And this, for example, can be implemented using map multi, which is an alternative implementation of flat map. By exploring alternative conversion, we can also compare the performance of equivalent alternative implementation of the same query. We will also evaluate the performance of parallel streams, since one of the most benefits of the Stream API is indeed easy-file parallelization. But we are also interested in supporting different query language which go beyond SQL. So, for example, NoSQL query languages with a MongoDB dataset, and supporting other output data processing libraries. So maybe not only the JavaScript API, but why not a Scala collection or a .NET link. And finally, we plan to generate a large benchmark suite and based on a more complex query than the one provided in the paper. Thanks for your attention. That's all with my tool, and here you can find both the tool and the benchmark suite.
So we have time. Yes.
Thanks for a nice talk. I wanted to ask, how do you do the join order? So you say if you have a select statement and you have three tables, A, B, C, and how do you convert these? Because how you join, there's different performance complexities. And this is my first question. And the second question is, can you handle the recursive SQL statement as well?
Thank you for your questions. So regarding the join order, this is actually part of the query planning phase. So this is not a component of our tool. So basically, we convert an existing query plan, and the query plan already specifies the order of the join. This is usually done by complexity, based on the selectivity, based on the number of tuples. And unfortunately, no, we do not support recursion here. We think a bit about that. We think it is possible. There is no reason why it shouldn't be possible, because there is a recursion in Java, so we clearly can do that, but we are currently not.
Okay. So this is really cool. I like it. But and you mentioned the limitation that obviously you're not covering all of the functionality of the Stream API. Is there not also a concern that perhaps there are certain kinds of applications you want to write the Streams API, which are not really captured by the kinds of queries that you write in SQL. Did you run into any particular examples of those kinds of things, or do you think that this is really doing a pretty good job of exercising all of the performance metrics that we care about?
Thanks for your question. I believe that for only for benchmarking purpose, once we cover all or almost all the methods in the Stream API, we can basically obtain enough information, enough metrics, even if the kind of application from a user perspective is very different. However, by supporting different query languages, for example, NoSQL 1, we could for sure expand the kind of application that we can support, even from a user perspective, but still limited in data processing.
Yeah. I mean, I can imagine in a sort of probably unlikely but sort of perverse world, you can imagine you put all this effort in, you put all these benchmarks across, and then you go, oh, no, we need to optimize this in this way. And then it turns out to be completely useless because the way in which users of the Streams API write their programs might be quite different to the way that the database is different. But I guess that's unlikely to be the case anyway.
I also guess unlikely, but anyway, it's a very good point.
It's a bit of the same point. So I was going to ask how idiomatic Java Stream API code is that you generate, which goes in the same direction. So extending it, carrying it further, are there any substantial corpuses of Java Stream API code that you could analyze to assess just how idiomatic your code is?
Well, I think that that is pretty tough to do. I mean, by analyzing, I mean by automatically analyzing this, whether the generated code is idiomatic. This would require more manual effort, for sure. So something that we can do, for example, is comparing the performance result that we obtain with our tool with, for example, the only free workload existing with the Renaissance benchmark suite, which is for sure idiomatic code, is not based on query languages. And so it's really very different. And we are for sure interested in also, for example, looking around in existing application, transform them into benchmark and analyze the result and look whether they are similar or completely different with the one we obtained with our tool. This is
stepping away from benchmarks and looking at tutorials of Stream API.
Yes.
Reading the tutorial would write your code.
Yes. If you go with tutorial, you will find usually extremely small streams with almost a SQL query written into Java, as for my knowledge. But maybe not. Maybe it's not the case for every application. For sure, it's not. Any application could be rewritten with the Java Stream API. So yes, it's not fair to say that we cover all practical usages of that.
Okay. So, any other questions? You want to ask? Do you want to ask more? Okay. So, let's start the speaker again.
Thank you.